Hello everyone. Previously we had discussed on the Tarjan's algorithm, right? So today we'll be discussing on the topic Tarjan's SCC algorithm, nothing but strongly connected components algorithm, right? So what does this one definition part say here? Let's see the same. So Tarjan's algorithm is used to find the strongly connected components, nothing but the SCCs in a directed graph. In a directed graph. So this is very important, right? So this is quite different from the normal one. The last one that we this one what do we call discussed basically. Right? So Tarjan's algorithm is used to find the strongly connected components, nothing but the SCCs in a directed graph, right? So an SCC or the strongly connected component is a maximal set of vertices. This is the maximal set of vertices where every vertex is reachable from every other vertex in the set. So each vertex that is present is reachable from every other vertex in the set, right? So whatever the vertex that we consider, basically, right? So this is fine, I believe. Next, let's move on with the explanation part here. So first thing here, Tarjan's algorithm is DFS based. Just remember this one. Tarjan's SCC algorithm is completely DFS based, depth first search based, right? So we know what is DFS. We have already discussed that one, right? We have solved many problems as well already, right? So this is fine, I believe. It maintains discovery times and a low link value for the each node. What it does, it maintains the discovery times and a low link value. These two things are very important. So while writing the code or while writing the algo, so you shouldn't be asking what is discovery time and low link. So it maintains the discovery times and the low link value for the each node, right? So discovery and low link value, what is it basically? Discovery time of V is nothing but the time when node V was first visited. For the first time, we will be visiting certain vertex, right? So that we will call as discovery time of V. And what is low link of V here? The smallest discovery time reachable from V, including itself. That we call it as low link of V. This is fine. A stack keeps track of the nodes in the current DFS path, right? So we'll be going with the iterative DFS. A stack keeps track of the nodes in the current DFS path. Just remember this one. Yeah. Now, whenever a node's low link is equal to the discovery time, we have found the root of a strongly connected component and we pop all the nodes from the stack until we reach this particular node, right? So this is fine, I believe. The algorithm efficiently finds all the strongly connected components on the big of V plus E time, right? So this is nothing but the time complexity. This is fine, I believe. Yeah. Now let's do one thing. Let's try to implement the same thing, whatever we discussed in the this one explanation. Now we try to implement the same thing in the form of code. The first step here would be let's import the default dict just for the easy adjacency list creation, right? So I'll just go with from collections import default dict, right? Yeah, this is fine. The first step here would be let's go with a graph class to hold the adjacency list, right? So I'll just go with class graph here. This is fine. The first step would be constructor or the initialization part, right? So I'll just go with init here. This is fine. Let me give vertices along with the self. This is fine as well. So first thing would be the number of vertices and the second one would be adjacency list. So I'll just go with the self dot v equals vertices. This is fine. The next one would be self dot graph. So this one graph. Let me assign this one to the default dict. Fine, default dict of list. Let me pass list here. This is fine. Yeah, this is nothing but the adjacency list. V is nothing but the number of vertices. So graph equals default dict of list, whatever we have written. That is nothing but for the adjacency list, right? Now we have to add the edge from U to V. So how can I write this one? Default add edge. This is fine. Let me pass cell U as well as the V. Right. So this is fine. Now self dot graph of U. Hmm, dot append. So just give me a second here. So let me go with append by. This was not showing in the this one suggestions actually. This is fine, man. Graph of U. what we are doing here, we are appending that one to the V. So this is fine. Now the next step, let's move on with the next step, right? So this def has to be here. So indentation problem. That is the reason this was not showing this thing, I think. Here, append. Now, just give me a second here. That was the problem actually. Yeah. Now let's do one thing. Let's go with one more function, main function, Tarjan's algorithm implementation. Let's go with the Tarjan's algorithm implementation, right? So I'll just go with one more class here. So this one will be class. So let me go with Tarjan SCC, strongly connected component, right? So this is fine. Now, what shall we do? So this one might be indentation problem as well. So let me go from here. This is fine. The first step would be again the initialization part, right? So this will be def init, and along with the self, I need graph as well. So this is fine. Now, there are so many things we need for the initialization. Basically, I'll just go with the self dot graph. So this one, let me assign this one to the graph. We need this. Yeah. Now, self dot number of vertices also we need again. So this one, let me go with the this one graph dot v. Yeah. Next thing would be index, self dot index. So this is fine. Let me assign this one to the 0, nothing but the time index, right? So next one would be self dot stack. So let me go with the stack here, assign this one to the empty array. The next thing would be self dot on here underscore stack here. Um, this one, let me go with false. This is fine. False into self dot v. Yeah, it's v itself, right? What is this? So this is fine now. This has to be multiplication operator. Now this is correct. Yep. Now we have to go with the indices as well. So I'll just go with here indices. So let me go with -1 into v actually. Yep. Now this is fine. We are left with low link as well. We'll be going with the low links as well as the low link as well as the strongly connected components, right? So I'll just go with mm, low link here. This is fine. So this will be same -1 here into vertices basically. Next, let's go with the strongly connected components here. SCCs. I'll just give here SCCs. Let's assign this one to the empty array. This is the list to store the strongly connected components, right? So this is fine. We are done with the what do we call initialization of the constructor part. Next, let's go with the DFS function man. So DFS. So I'll just go with def here. Let me go with strong connect. This is fine. Self comma C. Not C actually. I need vertex. This is fine. Yep. So within this function, what we'll be writing first again, there are so many this thing. What do you call? What do we call that one? Initialization. Let's initialize indices low link of v indices of the vertex. So low link of the vertex, this one, and also index. We have to append stack this one vertex to the stack, and then let's go with the on stack of that particular vertex. Let's set the boolean value true to further make use of it, right? So let's do these things very quickly. First, let me type this one quickly. Dot indices of v, assign this one to the indices, right? So this one index, sorry. Next one, low link of v, let me assign this one to the index as well. Yeah. The next one is index. Um, let me assign this one to the so this one will be self dot index plus one basically. Index equals index plus one. This is fine. Now I'll just go with the stack dot append. What we need to append basically vertex, right? So this one within the parenthesis. Fine. The next one is self dot. So I'll just go with the on stack here. On stack, on stack of vertex. Let me set this one to the boolean value true. This one we'll see why we'll be making use of this particular variable in the future, right? So now we have to explore all the neighbors. For that, let me go with the iteration part or the for loop. So this one will be for w. Uh, this one graph. Graph is fine. Let me go with a graph of v as well. Yeah. So let me go with a simple if condition. If dot indices of this one, what do we call indices of w? So if it is equivalent to -1, so then here node is not visited then, right? So that is the reason we are going with -1 here. Then let me go with this one, what do we call strong connect? So I'll just go with strong connect of we have to pass w, right? So this is fine. Next, let me go with self uh, low link. This is fine of vertex. Let me assign this one to the min of let me go with low link here. Low link of v. This is fine as well. Self dot low link again link of w. So this is fine. Yeah. So next let me go with the elif man else if. Right. So let me go with elif self on stack. This is also fine of w. Yep. So now self dot low link of v. Let me assign this one to the min of dot low link of v. This is fine. Dot indices. Let me consider indices of w basically. Right. So this is fine, I believe. Let me come out of this one entirely, man. Now let's do one thing. Let's go with the if condition, man. Yeah. So I'll just go with the if condition. If v is a root node, then we have to pop the stack and we have to generate the strongly connected component, right? So I can just write it on this way. If self low link, so this one of vertex. So let me assign this one to the indices, right? So let me go with indices here. This one indices of v. Yeah. Now what happened here? Why this is taking here, man? Is everything correct here? If I have to write it here, I believe. Now this will take us to the correct place, I believe. No? What's wrong here? So this is fine, right? If cell loading of v. Oh yeah, this one I have to write. This is we are comparing the value, right? So now this is correct actually. Strongly connected component. This one SCC. Let me assign this one to the empty array, right? So next let's go with a while loop. While true, right? So while boolean value true, then let me assign w to stack. We have to pop, right? We have to remove the element. I'll just go with a stack dot pop. Then let me go with on stack as well. So here on stack of v, right? So vertex. So let's set this one to the false now. Now after doing this, let's append this one w to the strongly connected component. Wait, actually SCC append. What we need to append here? W. Next, let's go with if w equals to v. So the value, let's break. We have to break from here, right? So this is also fine. Now let's do one thing. I'll just go with we have connected SCCs, right? Yeah, strongly connected components. Let's append the SCC to the SCCs, right? So this one I'll just go with SCC. Yeah, this is right. Now let's do one thing. 1 second. Yeah, we are done with this particular function, strong connect function, right? So now let's move on with a function uh, to get all the strongly connected components. So what shall I name this function? Let me go with, let's do one thing. Let me go with get strongly connected component or components. This is fine. Yeah. Now within this function, first thing is I'll just go with a for loop for v in range. I'll just go with self dot v. This is fine. Yeah. Now within this for loop, let me go with simple if condition. If self dot indices. So this one I'll just go with the indices of v. If it is equal to -1, then what we'll do? Let me go with, oh, why this is, oh, one second. I'll just go with self. But strong connect, we have already written the function strong connect. Let's make use of it and let me pass the v here, the vertex. We are getting all the this one strongly connected components here within the get strongly connected components function, get SCCs function, right? So finally, what we need to return here, we need to return this one self dot SCCs, right? Strongly connected components basically. Yep. Now this is fine, man. Yeah. Now let's do one thing. So here, let's create the graph and run the Tarjan's algorithm, right? So let me go with some example usage here. And let's go with the print statement just for the interactive purpose. I'll just get the example usage from the Google, man. Just give me a second here. So let me do one thing. Let me copy paste this one, right? So this is fine. We are just creating the graph and running the Tarjan's algorithm here, right? So this print is just for the this one interactive purpose, right? So we have the graph edges here. So it just, so I can just draw the graph and show it to you here. So we have from 0, 0 to 1, 1 to 2, basically, yeah, 2 to 0. This is one thing. 2 to 0, connected graph, right? 0 to 1, 1 to this one, directed graph, right? So 1 to 2, this one, this is fine. Then we have connected 2 to 0, this is fine. Then 2 to 3 actually, let's consider 2 to 3, the edges that we have considered within the example, 2 to 3. Then 3 to 4, this is fine. And 4 to 5, yeah, let me consider in this way, 4 to 5, this is fine. Then 5 to 3, let's consider this one, 5 to 3. Yeah. Next, 6 to 5 we have. So here we have 6 to 5. Then finally we have 6 to 7, right? So I'll just write it over here like this, 6 to 7, right? So this is directed graph. Yeah. So this is fine. We are just adding the edge here. This is fine. We are just calling the tangents. This one strongly connected algorithm. This one, whatever the algorithm that we have written. This class basically we are calling here, right? And passing the G, nothing but the graph. So this is this one again. The same thing we are calling this one. Uh, get strongly connected components. This one function basically. Then finally we are going with a print function for the this one interactive purpose strongly connected components we have to get here. So what is the output that we need to get here? Here basically we have the understanding of the algorithm whatever we did here, right? So strongly connected components that we need to get here is first thing is 210, right? 210. So this is one thing. Why if you would have no, if you know this one, this is fine. Let me explain this one step by step. 210. Also, we need to get the output. So here 543 as well, right? We need to get the output 543, and then finally we have to get 6 and we have to get 7. We have to get 6 and we have to get 7, right? So let me write this one within the another array, right? So let me mention this one. So why 210 here? So I have drawn the this one graph here. Just look into this one carefully. See here, nodes 0, 1, 2 from the this one, node 0, 1, 2 form a cycle and are mutually reachable, right? So 0, 1, 2, this forms a cycle. You can clearly see here. See here 0, 1, 2 again from 2 to 0. This one this forms a cycle, right? This forms a cycle, right? So node 0, 1, 2 forms a cycle and are mutually reachable. They are mutually reachable. So this is strongly connected component 1. We can just represent this one as 1. This is the first one, right? This one. Next one we have given this one 543. We know this one now why it is SCC. The second one 543. 543, this one I'm speaking of, 5, 4 and 3. This one, see here, 5, 4, 3, this part, right? 5, 4, 3. So nodes 3, 4, 5 form another cycle here. You can clearly see here 3, 4, 4 to 5 again for this one 5 to 3. So this forms a cycle, right? So this is nothing but the strongly connected component 2. We can just call this one as 2. The first one, this is the second one, SCC second one, right? So the third one here 6. So node 6, so this one 6 basically it is isolated from the cycles, nothing but the this is isolated from the cycles, node 6. This part you can clearly see here, right? So this is isolated from the cycles, right? So this one we can just call this one directly as the this one, what do we call, third one, strongly connected component, this one SCC, third one, right? Finally we are left with 7. 7, same thing, node 7 is isolated as well, right? Node 7 is isolated as well. So this one we can just call this one as 4, strongly connected component, fourth one, this one, right? So these are the 4 strongly connected components. First one is this forms a cycle 0, 1, 2. So this one we have represented this one here. The second one is this one 3, 4, 5. Right. This also forms a cycle. This one is the strongly connected component. Second one, second strongly connected component. Third strongly connected component is node 6. This one we have represented here. This one. Why? Because node 6 is isolated from the cycles. This is SCC3, nothing but a strongly connected component 3. Final one, the fourth one here is node 7, that is isolated, strongly connected component 4. Right. So the output that we need to get here is this one 210, 543, 6 as well as the 7 when we write the code. Right. So let me remove this one entirely. Yeah. So yep. Now as we have the understanding of the this one algorithm as well as the input output, let me run the code. So let's run whatever the code that we have written, right? So I'll just give Control J here. What shall I give here? Python. This is fine. Have Tarjan SCC object has no attribute. So this one has to be indices. What's the line number? 44. Yeah. So this one has to be indices. This is fine. So let me give clear screen here and run this one again. Yeah. Now we are getting the strongly connected components 543, 210. So we are getting 7, right? So 210 is fine. We are getting just 7, right? We are not getting 6 here. Just give me a second. So this one here, what mistake I have done? Why I'm not getting 6 here? So this one, due to this one. In the strong connect this one function. So what I have done here is, so this one has to be self on stack I have made use of. So here we have to pass W or not V actually what. So this one has to be wait actually. This is fine. Now let me give clear screen and let me run the yeah, now we are getting C 543, 210, 7 and 6. So order doesn't matter. You can get 6 or 7, but we are getting the correct ones, right? 543, 210, 7 and 6, whatever I have showed you uh, just recently, right? So this is the output that we need to get, and we are getting the desired output, right? So we know why we are getting this output, right? So this is fine. So now this is it about the Tarjan's strongly connected component algorithm. Now we are done with the algorithm. So next we'll be discussing on the, just give me a second here. Next we'll be discussing on the topic, this one, Codeforces strongly connected algorithm, right? Component, strongly connected component algo, right? So now we are done with this algorithm. Let me summarize whatever we have learned so far. Just try to remember these 2 to 3 points, right? So the first point here would be this one, Tarjan's algorithm. So 1 second, just give me a second. Yeah, this is fine. 1 second. Yeah, this one, Tarjan's algorithm, what it does, it finds all the strongly connected components, right? Using what it uses basically DFS, right? So just keep this in mind. This is very important. This one, Tarjan's algorithm, it finds all the strongly connected components using DFS along with the low link values and a stack actually, and a stack again. Let me tell you this one loud. Just listen to this. Tarjan's algorithm finds all the strongly connected components using DFS, low link values, and the stack, right? So it is efficient. It is time efficient. We know this. Running in, so what was the time complexity that we discussed? It runs in because of V plus E, the Tarjan's algorithm, right? Strongly connected component algorithm. Strongly connected components are crucial in graph theory. Just remember this one, the third point. Strongly connected components are crucial in graph theory, also in the circuit design and the dependency analysis. So these are some of the use cases where um, where are these things basically strongly connected components used. SCCs are crucial in graph theory, circuit design, as well as the dependency analysis. Just keep this in mind. So let me delete this one. Yeah. So these are some of the important points I found, so that I just wanted to discuss with you guys, right? Now we are done with the Tarjan's SCC algo. Next, we'll be discussing about this one on the topic Codeforces strongly connected component algorithm, right? For now, this is it. Thanks for watching, guys.